morning, everyone. Nice to see you all here. Thank you for joining us at the session Manufacturing and Testing of Electric Motors for the Automotive Industry. It's nice that you're all here. You probably think that we put on this webinar because we are at about 1/3 of the road between Coiltech in Pordenone in September and Coiltech in Ulm in April. So to give some opportunity of technical exchange to the market. And that's true. However, the real reason why we put on this webinar today is because yesterday we were joined by a new member of the team, Francesca Tisana. She will look after the exhibitors from Germany. So, Francesca, welcome to the team.
Thank you. It's a pleasure for me. Hi, everybody. Okay.
Thank you.
Thank you.
A good time in Coiltech.
Thank you very much.
So, after this little stint, let's come to you, dear participants of the session. Today, we are joined by attendees, by viewers from 38 nations. Together with the team from University of Aquila, who support us, cooperate with us for many years for the organization of the World Magnetic Conference, and now for a few months for the Electric Motors Talks. We are thrilled and excited about this intercontinental resonance. It's really great that you are all here. And we'll publish more details on the attendance within the following days. We switch directly now to a lecture hall in Pordenone, pardon, not in Pordenone, in L'Aquila, to Giuseppe Fabri, Dr. Giuseppe Fabri. Giuseppe, you have been involved in preparing the World Magnetic Conference for many years. What can the visitors of Coiltech in Ulm expect from the World Magnetic Conference in Ulm?
Thank you, Sebastian. Good morning to all. We organized the conference in 10 topics concerning the main technical aspects of designing, manufacturing, and testing electrical machines, for instance, motor, generator, and transformers. Of course, in this time, the hot topic is e-mobility, and we will find in Ulm not only presentation concerning the motors, electric drivetrain, but also energy storage and charging devices. About the conference organization, you will find 3 conference halls, and all the presentation will be the live in person and in English.
And who can hold a presentation?
We are inviting contribution from corporates and academic institutions. So we are expecting a technical presentation proposal within January 21st.
Okay, thank you, Giuseppe, for
this
update, and of course for all your help. Nice hello to your students, and good continuation of the lectures, and we keep our fingers crossed for the exams for the students.
Yes, thank you.
Note one thing that I would like to add is that there's no charge for the speakers or for the audience to participate at the conference. We know that this is an important piece of information for some of the participants, so I don't want to miss the opportunity to point it out. The director is now pasting some links to useful information concerning the conference, the sessions, the speakers' guidelines, so you can find everything that might be useful for you there. We are looking forward to receiving your presentation proposals and, of course, to your visit in Ulm. One person is in Ulm already today. Matteo, the exhibition manager of Coiltech, and he's there. Just a second. He's in Ulm to prepare for the show. So Matteo, apart from that's obviously cold in Ulm, what's the progress?
Thank you very much, Mr. Kuster, and hello to everybody. At the moment, 267 stands are booked. In February 2020, we decided to postpone Coiltech Deutschland. There were 224, which means that the growth is set to continue.
Where do the exhibitors come from?
There are very few other industrial trade fairs in Germany with such a wide international mix. 39% are companies from Germany, 37% from Italy, 20% from the other part of Europe, and 4% from other nations.
You said that the number of the report that you told us in press release growth is there no space for everyone?
Well, compared to the original plans in 2020, we now have 2 more halls, and in the future we can even add another one. In any case, the exhibition is now so big that we are even setting a new entrance, a second entrance for visitors.
Thank you, Matteo, for
welcome.
Your information, and well, good luck in today. And I hope that I see that you are dressed. Okay, I must have switched off the microphone. Sorry. Thank you, Matteo, for your update. And well, let's talk now a bit about the advantages of being at a conference, at a face-to-face conference. The main advantage of a face-to-face event is that one can interact each other with other attendees. This is not so easy at online event like this, but we have thought a little bit about what we can do to bridge the gap. To talk about this, we now switch to the visitor relationship office in at Coiltech to Anna James. Anna, what have you prepared so that the participants of today's session can interact directly with each other?
We have set up the chat functions so that all participants can contact one another directly, and this is until 2 p.m.
And what can the participants get to get in touch with each other after today's session?
Well, we have set up on LinkedIn a dedicated group called Coiltech Electric Motors Talks, and this is open only to participants in the Coiltech Electric Motor Talks. This offers the possibility to get in touch with one another directly, even if you're not connected directly on the platform.
And are there other advantages of becoming a member of the group?
Yes, actually there are. For example, the group members can find the contact details of the speakers in our posts. And we also publish the video registrations on YouTube in private mode. Afterwards, we publish the links of these videos into the posts of the groups.
Thank you, Anna. That's certainly all very useful. Thank you for your effort and for these informations. Now we switch back to L'Aquila, this time to Professor Marco Villani, the chairman of the World Magnetic Conference and of the Electric Motors Talks. Thank you, Marco, for chairing today's session as well. For all your support in all the years, and let's come to today's topic. Why is testing in manufacturing of electric motors so important, Marco?
Thank you, Dr. Kuster. Good morning, everyone from the University of L'Aquila, and welcome to this technical webinar on manufacturing and testing of electric motor for automotive applications. Your question is very interesting, but it's well known that the electric mobility represents now a possible solution to the pollution and global warming problems. And the impact of internal combustion engine on the environment has led to replace it by alternative propulsion systems, among which the electric machine has become the primary candidate. The electrical car market is booming, and in the next 20 years, a third electrical vehicle sales is expected, which should exceed that of traditional internal combustion engine cars. There is a great interest in finding propulsion systems with high power density, high efficiency, and low cost. And several types of electrical machine has been proposed for the current electric vehicles. The motor design requires the use of innovative sizing procedures and an accurate choice of the material in order to satisfy the hard requirements and constraints. These performances are guaranteed if the motors are manufactured and assembled correctly. The manufacturing process represents an important step, and this concerns the stator rotor cores, the insertion and magnetization of the permanent magnets, the stator winding manufacturing, and the final assembly of the motor. These processes are now automated to ensure a high quality of finished products, and several tests can be carried out during the manufacturing processes. This webinar will investigate in detail these aspects, and also the detrimental impact on the motor performance. Today, we have three interesting presentations by Senis, University of L'Aquila, and Physik. I would like to thank the speakers for their contributions, all the attendees for these electric motor talks, and also the staff of Quick Fair and my colleague, Dr. Giuseppe Fabbri, for their support in the arrangement of this webinar. We can start the section, and I invite the first speaker, Dr. Dragana Popovic-Renella by Senis. Good morning.
Good morning.
The title of our presentation is 3D magnetic field measurement of magnets, rotors, and motors. During the webinar, it is possible to submit questions by using the chat. Please, Dr. Renella, thank you again.
Thank you, Professor Villani. Hello, everybody. I'm Dragana Popovic-Renella of Senis, Switzerland. Our company provides advanced sensors and instruments for the measurement of magnetic field and electric current measurements. So we have two business units, the sensor business and the instruments business. Our sensor unit provides advanced sensor chips for the implementation in the customer's products, for example, for smooth motor control in robots and other applications. Our instruments business provides various test and measurement equipment, for example, for the accurate magnetic field measurements of magnets, rotors, and motors. And this will be the subject of my presentation today. So let me share my screen. In my presentation today, you will learn why Senis magnetic field measurement instruments provide you real and accurate 3D magnetic field measurements. I have some problems. Okay, sorry. So Senis sensors and instruments are based on the Hall effect. Let me recall what the Hall effect is. Briefly, it is an action of the magnetic field on electrical currents. So this picture shows a plate-like Hall device. The thin plate of conducting material is fitted with 4 contacts. So we have here the sense contacts and the current contacts. If a current is flowing through the plate and a perpendicular magnetic field is applied to the device, a voltage appears between the sense contacts, and this is called the Hall voltage. This is a classical Hall sensor that measures only the perpendicular component of the magnetic field. If we want to build a 3-dimensional sensor, we may compose such 3 classical Hall effect sensors in a cube, but the sensor's disadvantage is the large sensitive volume and the high non-orthogonality of the sensitivity axis of the Hall sensor. The founder of our company, Professor Popovic, developed the first so-called vertical Hall sensor, which is sensitive to the magnetic field component parallel to the chip surface. If we combine vertical Hall sensors and horizontal Hall sensors, we can build a real and pure integrated 3-axis Hall sensor chip with a very small magnetic field sensitive volume. Such 3-axis Hall sensors packaged as very thin Hall probes are, for example, used as the sensing probe in our magnetic field measurement instruments. So Senis not only invented the first 3D Hall sensor, but we also invented a new generation of 3D Hall sensors, the world's most compact 3D Hall sensor with highest magnetic resolution available on the market. So the high magnetic resolution is due to our patented vertical Hall elements that feature at least 3 times better signal to noise ratio than any other vertical Hall devices available on the market. The magnetic field sensitive volume is very small, only 100 times 100 times 10 micrometer cube. Well, why is this so important for your measurements? Because a magnetic field is a divergence-free vector field. This figure illustrates a strongly non-homogeneous magnetic field. So the orientation of the magnetic flux density vector and also its amplitude are position dependent. Accordingly, all 3 components of the magnetic field should be measured at the same spot. Therefore, the magnetic field sensitive volume of the Hall probe has to be very small. So here in example, the magnetic flux density vector is measured with 2 different Hall probes. Probe A has a large sensitive volume and probe B has a small one. So the measurement results will be the average of all magnetic field lines seen by the probe's sensitive volume in that area. So obviously the magnetic field measured with probe B will give us more accurate results. So this is simulated in this graph here. the figure shows the measurement of a sine signal of the magnetic field of an array of permanent magnets measured with a large and a small Hall probe. The amplitude of the magnets is 40 millitesla, the pole width is 1.3 millimeters, and the pole period is 2.6 millimeters. So these are some typical values for rotary shaft encoders in powertrain applications. So there is a difference in the measured amplitudes. The measurements which were average over a small magnetic field sensitive volume of a Hall probe are more closer to the real values. Now, a few words about the calibration of the Hall probe. The sensitivity axes of a Hall sensor are never perfectly aligned with a reference coordinate system. The resulting accumulated angular errors of the sensitivity vector can be of the order of 1 degree, and this is too high for modern magnetic field measurement applications. Therefore, the angular errors must be reduced, and this is done with calibration. So the Hall voltage of a single Hall element is given to the first approximation by the scalar product of S, the sensitivity vector, and B, the magnetic flux density vector. So for a 3-axis Hall probe, the above equation can be generalized. So the VH3 is the Hall voltage vector, S is the Hall probe sensitivity tensor consisting of 9 components, and B is the magnetic flux density vector. So the 9 components of the sensitivity tensor has to be calibrated in order to reduce the orthogonality error of the 3-axis Hall probe with respect to the reference coordinate system. So first, precise calibration of the Hall probe is performed in our accredited calibration lab. So here we see a setup of this calibration. So there, the magnet, the NMR Tesla meter, and the mechanical tool. So the 3-axis Hall probe is positioned into this setup from several different sizes. The Hall output voltages are measured, read, and then substituted into these equations. And the inverse matrix is then stored into the magnetometers memory. So this calibration process can be also performed by placing the Hall probe in our patented calibration cube that we provide to our customers. So the angular error can be reduced to below 0.1 degree. We know how to calibrate 3-axis sensors and magnetometers. As shown on the previous slide, we have a patented solution which enables to determine very precisely the orthogonality of the 3D Hall sensor, and the Senis calibration laboratory is ISO 17025 accredited. We calibrate in all 3 directions, also for higher magnetic fields. Due to compact, pure 3-axis Hall technology, vast know-how in signal processing and calibration, we set highlights. In our product solutions, we always combine some unique performances, such as the highest magnetic resolution with high accuracy and high frequency bandwidth. As an example, the resolution of our low noise 3D Tesla meter is 1 microtesla, and the accuracy is 0.01%. And the frequency bandwidth goes from DC to 5 kilohertz. And this is unique, particularly in combination with the high 3D spatial resolution of the 3-axis Hall sensor. And that's the reason why our customers say that Senis is moving the limits of the feasible in magnetometry and sensor technology. Our efforts has been awarded by the European Commission with the Seal of Excellence, by the AMA Innovation Award. And recently our founder and CTO, Professor Popovic, received the Lifetime Contribution Award from the UK Magnetic Society. Based on our unique technology, we have developed various whole magnetic sensors and measurement instruments for various applications in industry, for test and measurement, for position and speed measurement, current sensing, and this for various customer segments. So on the next few slides, I will talk about the magnetometers and the magnetic field mappers. We provide analog and digital Tesla meters and handheld 3-axis Tesla meters. For example, this 3D Tesla meter with highest resolution and accuracy is also used as a reference 3D Hall Tesla meters at various institutions such as CERN, the European Organization for Nuclear Research. For the automotive industry, we provide such 3-axis Tesla meters with a thin and compact 3-axis Hall probe with good accuracy, resolution, and bandwidth. So let me give you an impression of the 3MH3 Tesla meter with integrated 3-axis Hall probe, which is used in automotive industry. So here the Tesla meter is connected to a computer with an acquisition and visualization software. The Tesla meter is based on a high accuracy magnetic field to analog voltage transducer. It provides a temperature compensated output signal for each of the 3 components of the measured magnetic field, Bx, By, and Bz. A digital module is applied to the analog transducer, and it allows visualizing the measured values on a display and also by a computer. So the Tesla meter also provides analog output to connect to a customer's data acquisition system. So here are shown various Hall probes. We also provide compact sensor arrays and customized probes and packages. So the trend in magnetometry is to approach the object very closely with a pure 3-axis Hall sensor. And we approach the objects at below 0.2 millimeters distance from the magnetic field sensitive volume of our pure 3-axis Hall probes. That's also unique. Another equipment used in automotive industry is the Senis 3D magnetic field mapper with high repeatability and synchronization of the probe position and the magnetic field measurement. So Zenith Mapper measured the magnetic field of permanent magnets and electromagnets, rotors and motors by means of 3-axis Hall probes. For example, such disc and ring magnets that are used with position sensors can be tested. It is important to know how a magnetic performs in order to optimize the functionality of the entire magnet sensor system and motor. For example, we should know the error of magnetization, and we should select the good and bad parts in the production lines. So our 3D magnetic field mapper maps around the magnet and visualizes the 3D graphs of the magnetization and shows some analysis, such as the angle error or of magnetization at the inhomogeneity. It visualizes the magnetic flux density Bx, By, and Bz, and these values were measured at virtually the same spot. You may recall what I explained earlier in my presentation, that our 3D probes are composed of both horizontal and vertical Hall sensors, so that everything is so miniaturized and compact that you measure all three components of the magnetic field at virtually the same spot. And that's the reason why we talk here about pure and reliable 3D magnetic field measurements. Now, let me show a short video on the Senis 3D mapper to give you an impression on how we measure, for example, the angle deviation of magnets. So this is the Zenith Mapper with a mechanical moving platform. The 3D Hall probe is mounted here, and everything is connected to a computer for the control and visualization. So it is possible to easily interchange various Hall probes and magnetoresistive probes or eddy current probes for crack detection. Every probe has a smart touch sensor, and it is recognized by the mapper system. So now we measure here a dipole magnet with a 3-axis Hall probe. The magnet is rotated for 360 degrees, and during the rotation, all three components of the magnetic field are measured. So the real magnetic angle is calculated as arctangent Bx, By. At the same time, the encoder mounted under the rotary stage is measuring the ideal angle of rotation of the mapper. So the difference between the real and the ideal angle gives the angle deviation. So the Senis 3D mapper also measures the rotors and encoders and ring magnets. And the Senis Mapper software provides real-time and offline analysis. So we can set the data for good and bad parts. And the mapper also measures the entire motors. The compact 3-axis Hall probe enables the 3D magnetic field measurements in very small air gaps, and so supports the optimization of the electric motor performances. Here are some visualization graphs of the measured magnetic field data. The software generates a 3D map of the magnetic field, counts number of poles, calculates pole width for multiple magnets and rotors, detects zero crossing, measures magnetic angle, and much more. Here are shown some mappers, various sizes of mapper, the standard, small and large mappers. We provide for various motor sizes, various mappers. So for example, for very small miniaturized ones, but also very large ones, such as 60 kilograms and more. Recently, we delivered a very large mapper for objects that are 1 meter diameter. We also provide test and measurement services, characterization services at Senis. And here is shown a nice customer reference. We are proud that Porsche in Germany applies the Zenith Mapper for their measurements. Several other companies worldwide apply the Senis mappers, Tesla meters, and sensors. For example, Maxon Motor, Bomatec, Melexis, and many others. Our headquarters is in Switzerland, but our presence is global. I would like to thank you for your attention and for trusting us.
Thank you, Dr. Popovic-Renella, for your interesting presentation, interesting contribution. We have some questions from the audience. The first one by Professor Chiricozzi. Are the measurements made during the motor operation?
Yes, of course. Our mapper measures both DC measurements, static, and measurements on higher frequency. Yes, it can be done.
Another question. Do you have an inspection equipment for entire electric motor test, including magnetic and electric performances?
Yes, this is a good question. We have developed a concept for the test of the entire electric motor testing, including magnetic and electric performances such as current and voltage, resistance, and crack detection. So we are currently discussing with a very reputable automotive company in Germany. The details will follow later.
Okay. Another question by Hamil here. What is the maximum diameter of rotor magnetic field can be mapped with the 3D mapper? Mm-hmm. What is the maximum rotor?
Yes, I answered this question already in my presentation. So the latest mapper that we delivered was for the objects that are of 1 meter diameter. So we can build very large mappers with the small 3D hole probes.
Okay, last short question. How flexible and adaptable is your mapper software?
Our mappers and the mapper software is used as test and measurement equipment, but also as production equipment. So the mapper software can be applied for these applications. And in addition, we also provide specific customer solutions, some software modules for various customer needs and applications.
Okay, last question from the audience by Davide Angrilli. What is the maximum temperature?
Of the hole probes, let's say the standard temperature is going up to 45 degrees, but we can calibrate also higher temperature for 120 degrees in-house.
Thank you again, Dr. Popovic-Renella, for your contribution. Thank you
very much for organizing this session.
Thank you. And see you in Ulm in April.
Yes, of course. Bye-bye.
Bye. Okay, I invite the next speaker, Dr. Andrea Credo from University of L'Aquila. Good morning, Andrea. The title of his contribution is Robust Design of Synchronous Reluctance Motor for Automotive, a focus on the manufacturing tolerance. Please, Andrea, you can share the screen.
I try to share my screen, but seems that I can't. Okay, share my screen.
Okay.
Okay. Good morning to everyone. I'm Andrea Credo from the University of L'Aquila, and today I present you the robust design of synchronous reluctance motor for automotive application. This is a focus on manufacturing tolerances in order to have the most robust design. Our university, our research activities are based on the designing, the prototyping, and the testing of innovative electrical machines and drives. We work on different applications such as the aerospace application, automotive application, domestic appliances, and so on. I focused my research on the design and control of synchronous reluctance motor. Today, starting from a short background and research goal, I will present to you the robust design of synchronous reluctance motor. The first step for the design is the optimization, and thanks to the optimization, we can evaluate several minimum of the function, and on this minimum, we have to select the most robust design. In order to make this, we have considered the manufacturing tolerances of the machines that affected the design of the machine and so on its performance. After that, we have evaluated these effects using a statistical tolerance analysis in order to evaluate the distribution of the parameters of the performance of the motor considering the manufacturing tolerances, and then we have considering that the motor is not a single pieces, but is made by a laminated core. Then we have evaluated a batch of machine in order to have a distribution of the performance of a batch of machine considering the laminated motor core. And finally, we have used another tool to evaluate the most robust design, which is the worst case analysis. Using these two tools, we have the item to use for the selection of the robust design, and finally we have some conclusion. This slide shows you the trends of the electric vehicle market, and we can see that the electric vehicle market is continuously growing despite the internal combustion engine market. In the next year, we expect that the sales of the electric vehicle can be very high and comparable to the ones of the internal combustion engine. The problem of this is the availability of the raw materials for this kind of machine. In this slide, we can see some electrical car sales in the market, and the most of them use the rare earth material. The problem of this material, which is the high and volatile cost of the permanent magnets, that makes uncertain their long-term availability, especially because the electrical traction technology is called to use for a large mass production. Therefore, there is a growing attention to alternative solution that includes rare earth-free materials, rare earth-free machines, or with a reduced use of the rare earth permanent magnets. In this, with this scope, we have analyzed the synchronous reluctance motor as a new traction technology to substitute the permanent magnet one. In this presentation, we have focused our research on the improvement of the robustness of the performance of electrical machine. And this is made considering neglected features such as manufacturing tolerances and deviations in the material properties. This is increasingly demanded because the manufacturer wants a robustness of the performance in order to can declare some requirements. The availability optimization procedure typically do not account for manufacturing tolerances, leaving the decision process incomplete. In this research, we have to propose some decision process for the robustness of the motor, starting from an optimization which accounts several local minimums, and in each of them we have evaluated the statistical tolerance analysis in order to evaluate the impact of the manufacturing tolerance on the machine performance. After that, we have also made a worst case analysis in order to evaluate the worst case of each local minimum. The synchronous reluctance motor can be used as a rare earth-free motor solution for the next generation of powertrain because it has some advantages, such as very low losses in the rotor, also at high speed, and this can be traduced in less requirement for cooling. The motor is attractive from an economic point of view and is very simple to manufacture because compared to the other kind of machine, the rotor requires also the punching procedure. But the motor presents several drawbacks, such as the structural integrity at high speed is difficult to reach, and we have to introduce some elements in the rotor, such as the radial ribs, that reduce the performance of it. The motor has a low flux weakening region, especially if the motor is used for high speed and the radial ribs are introduced, a lower power factor compared to the other kind of machine, and it requires an accurate design in order to obtain a very high value of silency ratio. The case study for this presentation, we have used a synchronous reluctance motor with flat shape barriers and flat wire. The equation of the fluid shape barrier are shown in the figure, and from this geometry we have get the preliminary designed with some analytical expression in order to evaluate the main parameter of the motor and the rotor. After that, we have carried out a design optimization. Starting from the preliminary motor, we have considered several starting points, and on these points we have make a local optimization. This is possible, and we have obtained several local minimum, one for each starting point that we have used. The best local minimum presents a strong reduction of the torque ripple reported in the slide compared to the preliminary one. We have preferred to make this evaluation considering the per unit and the per unit compared to the preliminary design in order to have a generic comparison of the performance. The best local presents a lowest torque ripple and a good average torque, and the constraint above outer space is satisfied. Here we can see the geometric, the design of the different local minimum and of the best local minimum, and each design are different from each other and present different value of torque ripple and average torque. If we don't considering the manufacturing tolerance, the decision process is finished and the best local minimum is the motor that we want to realize. But the manufacturing tolerances affect the stator and the rotor core, and the value of this affection depends on the manufacturing process. In particular, from the manufacturing process can depend the value of the tolerances that we have. The tolerances are typically a bilateral distribution, can be expressed as x plus man, the value of the tolerances, and we have considering that these tolerances affect the motor. The affection of the motor is the same for all the dimensions of the motor. After that, we can get the statistical tolerance analysis, and to make this, we have adopted a Monte Carlo analysis method coupled with a 2D finite element tool. For each distribution of the manufacturing tolerance in this study, we have considering the normal distribution, so the Gaussian one, and we have repeated the procedure over a batch of 2000 machines. So for each machine, we have considering the design data that we changed according to the manufacturing tolerances. The blue curve that we have here is the result that we obtained on the 2D analysis. The typically the machine are realized with a laminated core, so each lamination could be different from each other. The blue curve considered that each lamination is the same, while the green curve considering that each lamination is affected differently in terms of manufacturing tolerances. So each lamination is different from the other. To make this, it is possible to evaluate with a 3D finite element models, but the evaluation is very difficult and is time consuming. In order to make this evaluation, we have considering different lamination and we have averaged the effect of the lamination in order to have the green curve. We have repeated this procedure for all of local minimum that we have found with the optimization procedure, and we obtained for the torque ripple these curves. The best local minimum that which presents the minimum value of torque ripple when the geometrical data are ideal and without the tolerance analysis. When we considering the tolerance analysis, the best local minimum begin the worst of the worst in terms of torque ripple, while the local minimum 3 and 5 presents a short variation of the torque ripple and a minimum value 1. These the minimum value of the best local minimum are higher than the one of the local minimum ones because we have considering that the machine is laminated and each lamination are different, as I say before. So if we consider this curve again, here there is the minimum value of torque ripple for the best local minimum, but when we considering the lamination, the laminated core effect, the minimum value of torque ripple is moved in this direction. If we consider a machine with a very high number of lamination, this curve coincides with the average of this one. The same analysis has been made also for the torque and the voltage. For the torque, the best local minimum maintain a high value of torque, and we can make the consideration that the manufacturing tolerances affects more the torque ripple compared to the average torque one. So in the case when we want to minimize the torque ripple, the manufacturing aspects are very important. Here we can see the results in terms of voltage, and we can see that the local minimum 4 doesn't satisfy anymore the constraint of the voltage, which was imposed to 1 per unit. In order to compare the different design, it is important to use a single value, which can use as comparison. In our case, these single values has been obtained as the intersection between the cumulative distribution and an arbitrary value C. What it means, this data that we can obtain? This give us the indication of the percentage of machine that satisfy this value of torque. So if we use as C a value of 5%, we can say that the 95% of machine that use as geometry design the local minimum 5 has a torque ripple lower than the 42%. When we consider the best local minimum, this value is higher than 0.49. A further approach proposed for the selecting of the robust candidates is the investigation of the worst case performance. This method involves a search algorithm in order to evaluate the worst case one. After that, we can consider the most robust design, the one that presents the best worst case. The search algorithm typically have a high computational time, and this time is not constant. In order to reduce this computational time, we have carried out before the worst case analysis a sensitivity analysis on all the design variable. This is useful to define a set of main variables that mostly affect the performance of the machine and make the search of the worst case analysis using only these variables. From the result, we can see that the best local has a very high value of worst case, which is similar to the one of the preliminary design, but there are three candidates that presents a lower, a better worst case. Local 4, for example, doesn't satisfy the voltage constraint, and it can be discarded as the project because it can guarantee the performance, the required performance for the machine. Now we have proposed two methods for the selection of the robust design, and we want to select the best one between them. This depends from the application. If we want to guarantee a minimum value of torque ripple, or we can obtain a good value for a batch of machine. But we can use together these two methods. For example, from the statistical analysis, in this case, we obtained that the local 3 and the local 5 guarantee the best performance, while from the worst case, we have identified the local 1 and the local 5. Obviously, the local 5 is a project that be evaluated in both the method, and we can say that this is the most robust one. Here we can see the design procedure, and starting from the machine modeling and preliminary design, we have selected the design variable according to the one that typically are selected. After that, we have made an optimization on this in order to obtain the best local minimum and 6 local minimum and also 6 local minimum. In parallel with it, we have made the sensitivity analysis on the preliminary design in order to evaluate the most affecting variables. And after we have the information of the optimization, we can work in parallel way from the statistical performance analysis and for the worst case analysis. From the statistical performance analysis, we have the robust candidates, and the design selection we can use. We can move according to the result of the statistical performance analysis and from the worst case one. After that, we obtained the robust design of the machine. Therefore, a methodology for the selection of the robust design toward the manufacturing tolerances is identified by an optimization procedure as presented. The statistical analysis and the worst case research has been adopted for the scope, and the result has been presented and discussed. This approach refers to the manufacturing tolerances of the lamination of the synchronous reluctance motor with flight-shaped barriers. I conclude my presentation, and thank you for your attention.
Thank you, Dr. Andrea Credo, for your contribution. We have received some questions by the audience. The first one by Kunal Dugvekar. He asked if Eni is using this machine for traction application, and particularly for trams or train of around 200 kilowatt, 50,000 RPM approximately.
We have evaluated this kind of machine, similar machine for automotive application. We have evaluated the machine with 200 kilowatt of power, but we have used a higher speed. The maximum speed are set to 18,000 RPM. the solution, in order to make in order to be competitive with the other one, we have to use higher speed in order to improve the power density of the machine. Obviously, for the high power and the low speed, this machine is not indicated for the scope, and other kind of machines, such as the axial flux machine, for which present a higher torque density, is more indicated for the application at low speed.
Another question by Ravi Nagarai. What is the optimum dimension of ribs and bridge thickness of rotor lamination?
Okay, for the ribs, and we want that the ribs are the minimum as possible, because they affect always in for the degradation of the performance. But the problem is that that elements are necessary for the mechanical integrity at high speed of the machine. Therefore, the optimum depends from the application in terms of speed and rotor dimension. In order to make this, we have evaluated some tools. One of them is the Topology Optimization. Is a tool that allows us to minimize the mass inside the barrier in order to guarantee the integrity of the rotor. This minimization of the mass is useful for the minimization of the impact of this element on the performance of the machine.
Okay, another questions. Have you considered other distribution on the tolerance compared to the Gaussian one? Which is the difference in your opinion?
Okay, we have considered the Gaussian distribution because is the most used, but we can use also the uniform distribution, for example. But in terms of result, when we considered that the machine is produced with lamination, the effect of the distribution compared to the other are a higher dispersion of the distribution. But for the worst case analysis, all distribution are the same because the limits are imposed are equal.
Okay, another question by Komil Okak. What should be taken into consideration to power factor improvement?
Okay, in order to improve the power factor of this kind of machine, there are two methods. The first one is to have a control that maximize the power factor. These machines are typically controlled using the MTPA, the maximum torque per ampere. But this control presents a lower power factor. In order to improve it, we can use a higher angle control, and we can improve this value. But in terms of design, in order to improve the power factor of machine, we want to maximize the silencing ratio of the machine. But this is already the aim of the scope, because the maximization of silencing ratio maximize also the torque per current and maximize the power factor. And there are not other solutions to improve the power factor of this machine. Also, we can use, for example, in this machine, we can use another type of machine, which is the permanent magnet assisted machine. So we can insert inside the ferrite magnets in order to improve the power factor of the machine.
Okay, another short question. In your opinion, the synchronous reluctance motor, can the synchronous reluctance motor represent a valid alternative for the future electrical vehicle, respect to the permanent magnet solution?
Yes, but these depend from the application, because the main problem of the synchronous reluctance motor is the low flux weakening capabilities. Therefore, if the machine requires high performance in terms of acceleration and maximum speed, the synchronous reluctance motor doesn't be designed using the power minimization of the motor in order to satisfy the car requirements. And for it is have to be used the minimization of the torque. But this produce a oversizing in terms of power of the machine, and the machine is oversizing in terms of dimension and phase current. But if we use the machine in a city car, for example, or car that doesn't require high acceleration performance or higher maximum speed, the synchronous reluctance motor can be competitive with the other kind of machine.
Okay, I see another short question by Eva Teresa Cernacalvo. Was the efficiency someone considered in the optimization?
Okay, in this case, the aim was focused on the torque ripple minimization, therefore the efficiency is not taken into account, but it is possible to make similar evaluation with considering the efficiency as the objective of the optimization and maximizing it.
Thank you, Andrea, for your contribution.
Thank you.
Thank you. And I invite the next speaker, Mr. Fredric Wigh by Magnet Physik. Good morning, Fredric. The title of his presentation is Efficient Magnetizing of Large Traction Motors.
Exactly.
Please, good morning.
Thank you, Mr. Professor Villani. Yes, I'll try to share my screen here. Like that. Thank you very much. My name is Fredric Wigh. I'm from Magnet Physik, a known company. We work since 45 years in the business of impulse magnetization and measurement of hard and soft magnetic materials. The title of my talk today is Efficient Magnetizing of Large Traction Motors. And the talking points of my presentations are permanent magnet motors in traction applications. So first, some general information of where they're used. Then some information on different types of designs and some explanations why rotors look like they do. From there, we move on to in-situ magnetization with some of its benefits and for sure the definition. And after that, we consider the magnetizing circuit and also to end up in the showing of how we can increase efficiency during magnetization. As some presenters already said, the emission restrictions and climate change is transforming the mobility sector, not only in the automobile world where Tesla is leading the charge, but also in transport, air and marine sectors. And for the traction applications, there seems to be three distinct areas for motors. So we see the traction motor used in a battery electric vehicle as the main motor. We see an electric axle where a smaller traction motor is used together with an internal combustion engine to support it. And we see the serial or parallel hybrid variant where the motor is assembled close to or on the ICE to support it during peak load, but also to function as a generator or an engine brake to charge a battery when the vehicle is decelerating. And as was mentioned already, some of the benefits of the permanent magnet motor is that it's compact and light for its performance. And this is, of course, good in a vehicle where weight is an issue. The motor is very powerful, yet very controllable. So the torque and power density can be high, and you can have a very fine control, which is also important in a vehicle where every control input translates into the vehicle behavior. The motor is very efficient, which is good for range anxiety and battery sizing. And as we know, people are very keen on having a long range for their electric vehicles. So efficiency is very important. And last but not least, the motor normally has an overload capability, which means the motor can be designed for normal operating points. And if some more torque is needed, the motor can be overloaded for a short period of time to still satisfy the requirements of the vehicle. Sorry for that. The design considerations, permanent magnet motors are nothing new for vehicles. They have a very long history as auxiliary drives in vehicles. They are used in, for example, power steering, electric fans, electric windows and seats, and also for the door and trunk lid. But these are all motors that are used for a very short period of time. So no one is continuously moving their seats back and forward or continuously using the electric windows. And as that, they are very, they're very sensitive. They're not very sensitive to efficiency. And now that you use it for a traction application, it's very, it needs a different approach. Yeah, the approach has to be on efficiency because the motor is in constant use. You have to have thermal considerations to take into account because the motor is used for a longer period of time. So also needs to be efficient in that sense that the cooling is good, and it also has to be able to work over different ranges. So what are the main points for the design? So there are a lot of, for sure, there are a lot of design considerations for traction motors, and I'm not going to go into all of them. We heard some in the last presentation where things are considered like torque ripple, efficiency, and things like that. I've listed 3 areas here, which are also important for the rotor design, and in the end effect also important for the possibility to magnetize such a rotor design. So the first consideration is, of course, speed versus torque. So a high-speed motor tends to have a lower pole number than a high torque motor. Based on the diameter of the rotor, the pole number directly influences the pole width and the distance between the poles as well. So it's very important for the ability to magnetize such a design. Second important issue is the magnetic flux versus the amp windings. So the larger the magnet volume in the motor is, the higher the air gap flux can be, and the motor can use less current per unit torque. But it's more expensive because there's more magnet volume inside, so more money to spend on magnets. And of course, adding a lot of magnets into the rotor will make the motor prone to saturation. And this is, of course, lowers the efficiency of the motor as well. And the third point that I listed here is the skewed rotor versus the straight rotor. So by skewing the rotor, you can ensure a low cogging torque and maybe a sinusoidal back EMF, but it can cause axial forces, and for sure it has lower peak performance than the straight rotor. And from just these 3 things, you can see that there are a lot of different designs. But what are the results? Astoundingly, the results are not that different. We get constraints that lead to 6 points that I listed here. So the pole number is from around 6 poles up to 24 poles, a little bit depending on the speed of the rotor. The rotor diameter normally above 150 millimeters up to 300 millimeters. The stack height as well, from about 100 millimeters to 300 millimeters. As mentioned before, all magnets are neodymium iron boron, or most of them are, and they're mounted interior inside the rotor. The magnet grades based on energy contents is N35 or up to N42. And the temperature grades range from SH up to UH, a little bit depending on the positioning of the magnets and on the usage, of course, of the motor. And the power finally somewhere between 50 kilowatts and 400 kilowatts. But this list could even possibly be more condensed. For sure, the pull numbers are more in the range between 8 and 12. And the rotor diameter between 150 and 200, and the stack height maybe from 150 to 200. And I would guess right now that would include maybe 80% of all traction motors that are being built. Of course, it's going to be interesting to see what the future brings, where more and more designers get into this theme, and also what different designs can be done. So, enough with the text. So what does this look like? Well, I made a little sketch to avoid being sued or telling too much, since this is all NDA material. I sketched out some typical magnet placements. And you can see here the typical straight shape, which is known. You can see a U shape or a U shape with a bar magnet on top. There's the V shape magnet or the double V shape, and also more of a triangle shape. And this is all things that we see for customer projects. I'm not really sure why they all do the difference in the designs. I'm guessing they want to increase the air gap flux or possibly also use some reluctance torque from the rotor. In the end of the day, all designers have to decide which design to use that fulfill their specification. So now that was the part of the rotor, also the thing that we need to magnetize. So what about the in-situ magnetization? So the definition of in-situ magnetization is the magnetization of magnets after the assembly into a product. And already from the definition, you can hear that this has a benefit. For sure, you can introduce the magnets not magnetized. So this lowers the cost of the magnets, their transport and their storage. For sure, for magnetized magnets, some say as much as 80% of the packaging volume is just packaging material. And if you air freight the magnets, of course, you also have to consider the IATA 953 dangerous goods requirements. So that makes it even more complicated. Assembling non-magnetized magnets into a rotor is much simpler than assembling magnetized magnets into a rotor. So the assembly machine that puts the magnets into the rotor can be much, much cheaper. The third point is also important. Work safety when we work with magnets is of course a very important point. And as it is, no one can visualize if a magnet is magnetized or not. If you see a magnet, you can use some kind of measurement equipment to see if it's magnetized or not, or you can hold it against something metallic. But at the end of the day, by just looking at it, you cannot see if it's magnetized or not. And if you are sure to use only unmagnetized magnets, handling of them is much safer and much better. And last but not least, the cleaning of parts and processes is much easier when parts are not magnetized. This enables you to clean the magnets, but also the product itself in a normal way. And in that case, also remove metallic residue, something which is almost impossible once the rotor is magnetized. So now we have the rotor design. We talked about that, and we talked about the in-situ magnetization. So let's talk about the details of magnetization, something about the drivers of magnetic field and something of the inhibitors of the magnetic field. So again, I made a little sketch to ensure that it's visible. So the drivers of the magnetic field is for sure, first and foremost, the windings inside the magnetization fixture. You can see them here in orange. And for the windings, of course, the impulse current and the number of windings are the main influencers for the generated field. The rotor and the fixture both use laminated steel, so that helps us lead the magnetic flux. You can see it here on the little arrows. And of course, you can see W and H here, so the width and the height of the winding are, of course, also a way for us to shape the influence of the magnetic field, both its strengths and its direction. But unfortunately, there's not only drivers inside the magnetization fixtures, there are also inhibitors. So the number of windings and the rotor diameter and the rotor length are for sure inhibitors of the magnetic field. Higher number of windings and a larger rotor diameter and a longer fixture means that resistance and inductivity of the magnetization fixture increases. So you need more energy to drive the impulse current through the fixture. I also noted the iron circuit here, also in the inhibitors, because as well as helping, it's also hindering us since the iron circuit will go into saturation, at least at the heights of magnetizing field strength that we're looking for. And the third point you can see here, designated by S1 and S2, so the distance from the winding to the magnet. And it's easily comprehended that if the magnet is closer to the windings, the magnetizing field is higher. If the magnet is further away from the winding, the magnetizing field is lower, or we need more field to make sure that we reach the magnetizing field strength that we want. So now we have the data of the rotor, we have the data of the magnetization fixture and its inhibitors and drivers of magnetic field. So let's now move on to how we generate the current into the system to ensure magnetization of the rotor. So the current is generated by a capacitor discharge in a very simple circuit that can be seen here. So on the right, we can see the magnetization fixture with its resistance and inductivity. And once the magnetization fixture is optimized for the magnetizing of the rotor design, we need to consider the complete circuit to see how to generate the needed current. And of course, here's also the point where we talk about efficiency, because current can be generated in different ways. The setup is a very simple RLC circuit. So you can see the resistance R and the inductivity L dominated by the magnetization fixture. And you can see the capacity from the magnetizer and the charge voltage of the capacitor. And the charge voltage depends on the charge electronics, but of course also on what kind of insulation we have for all the windings in here and for the rest of the magnetizer for sure. In our case, we use 3000 volts, which we feel is a good level of voltage, not too high, not too low, to give us a good magnetizer sizing. So what about the efficiency? Well, the efficiency is defined as the ratio between the stored electric energy in the capacitor and the peak magnetic field in the magnetization fixture. So, and the peak magnetic field in the fixture is of course direct related to the peak current that we can generate in the magnetization fixture. So for the highest efficiency, there is a suitable combination that lets you maximize the current for the amount of energy stored in the capacitor. We can see here the proportions. So efficiency is proportional to the inductivity, to the inverse of the resistance, and to the inverse of the capacity. So what are the possibilities for us here to increase efficiency? Well, we could control R and L independently. That would be good. Then we could have a higher L and a lower R and increase the efficiency. But that's not possible really, because the resistance and the inductivity are all based on the magnetization fixture. For sure, we could get more energy by lowering, or we could get the same energy but lower the capacity and increase the charge voltage. This is possible, but the problem is if you increase the charge voltage, you also have to increase the insulation level. And by doing that, you tend to put in too much space into the magnetization fixture and not to be able to fit the number of windings that you really want. So how to solve this problem? There's a thought experiment. What if the winding number could be reduced by 50%? If we reduce the winding number by 50%, we can reduce the resistance and the inductivity by almost as much. And if we use a constant voltage and a constant capacity, no constant voltage, and reduce the capacity as well, then we increase the efficiency. Yeah, this means that we can get a better working system. But if we cut the number of windings into half, we need to increase the current by 2 to keep the same field strength. And this is possible up to a certain extent. There's only so much current that the components inside the magnetizer and inside the fixture can handle. So this helps for a while, but after a while you come to a point where you cannot increase the current anymore. So how do we do it? Well, how about instead of reducing the winding number by 50%, we just cut the winding in half. And this is what we call a multi-channel magnetizer. So what does this look like? Well, we see the same figure as before, but now divided into 2. So we have half the resistance, half the inductance in the fixture, and half the capacity in the magnetizer. The voltage stays the same. And to clarify it, we see again the blue square that shows us the magnetization fixture in a mechanical sense. And we see here the result of the efficiency increase. So the efficiency increase by reducing resistance and inductivity is in fact higher, it's more than what we reduce it with. So we actually need less capacity to drive the same current through the system. So a little showing a little current for this. So this is the reality. We have a magnetizing fixture for 10-pole rotor, diameter of 200 millimeters, and a stack height of 100 millimeters. And the impulse current that we need to magnetize this rotor is 20 kiloamps. And here we can see a clear difference. The blue curve shows the magnetizer with 1 channel, and it has 60 kilojoules of energy to enable us to give a impulse current of 20 kiloamps. This is enough to magnetize the rotor, so it would be a perfectly viable way of magnetizing said rotor. If we divide this into 2 channels, we can see the orange curve. And this shows a magnetizer with 2 channels where each channel has an energy of 25 kilojoules. So The magnetizer has a total energy of 50 kilojoules, and we can see that the current actually exceeds the needed 20 kiloamps and reaches about 23 kiloamps in the peak. So with 16.5% less energy, 60 to 50 kilojoules, we can still reach about 15% more current. And this is a great thing. Unfortunately, it doesn't mean that we can get 15% more field. Due to saturation effects and positioning in the fixture, we can only get a little more field. But still, the potential is, of course, for one thing, you can have less energy and reach more current. Or if we reduce the capacity even further to ensure that we reach the needed 20 kiloamps and nothing more, we end up with an energy saving between 16.7 and 30% for the same magnetization result. So to conclude, I think I'm a little bit late on time here. To conclude, large traction machines can be magnetized in situ. The multi-channel approach can increase efficiency of the magnetization significantly. And there are two benefits of this. One is, of course, the saving of energy. And the second is it can be used to magnetize designs where a one-channel magnetizer would not be able to generate enough power or current. And last but not least, the use of the magnetizer is no different from a standard magnetizer. You can see a picture of a fixture here. The only thing is we need to connect 4 cables instead of the normal 2 cables to run the magnetization fixture. Thank you very much for your attention, and I leave the field open for questions.
Okay. Thank you, Mr. Wigh, for your interesting contribution. We have received some questions from the audience. The first one by Alvaro Alonso. Do you have temperature simulation measurement to justify the motor temperature grades?
No, we don't. I wish for sure after the webinar we can discuss this face-to-face. But the temperature grade of the magnets are very closely linked to the usage of the motor, which is not something we simulate. For sure, I can also recommend our course from the Physik Academy, an online webinar for magnets technology, where we talk a lot about magnetization, but also about coercivity, demagnetization by temperature. Very good course for electric motor designers.
Okay, another question by Professor Chiricozzi. In the magnetizing in situ, do you take into account the mutual influence?
Excuse me, what influence?
The mutual influence.
Yes. The mutual influence between the fixture and the rotor, and also between the windings, winding to winding. Yes.
Yes, of course. Another question by Roberto Santarossa. In terms of motor performance, which is the difference in terms of magnetic flux value between magnetizing the ferrite magnets inside the rotor and outside before the insertion in the rotor?
So for ferrite magnets, there is not much difference. There's not much difference. The flux density needed is about 900 to 1,000 kiloamps per meter, and ferrite motors seldom give any problems for in-situ magnetization.
Yes, another question by Roberto Santarossa. The rotor lamination tolerance can affect the magnetization results?
Theoretically, yes. Practically, no, because of course, the magnetization is a different game than if you run the motor in series production, right? So the tolerances of the magnetization fixture are very tight because we only build 1 or 2. It's not a major, it's not a serial production in that sense. And for the rotor, we always simulate the magnetization for the complete slot where the magnet can fit in. So it's not based on magnet tolerances.
Okay, another question by Tong Wu. Can we also change the value of R and L by connecting them in series or in parallel instead of changing the number of turns?
Yes, theoretically, yes. But as magnetization is always a game of having a lot of current and a lot of windings, it's parallelizing is not very efficient.
Matteo Spaggiani asks, is there any restriction in terms of minimum distance between the poles on the rotor?
Yes, there is for sure. The distance can be 0, and then it very much depends on the positioning of the magnets, how the magnetization results will be. But basically, there's no limitation. It all has to be verified by simulation for sure to see what can be reached. And yeah, it goes into very much detail to figure out a very good solution.
Okay, we have received also several questions. We have not any time, but you can replay by using the chat. I have only a question for you. Does the increase in efficiency also generate other benefit during magnetization?
Yes, not only does it generate the let's say the same magnetization for less energy, it also lowers the heating of the magnetization fixture, which is always a good thing if you are in a series production where cycle time is of the essence. So basically you can do with one fixture instead of 2 or 3 fixtures with less efficiency and less cooling.
Thank you again, Mr. Wing, for your contribution. And
thank you.
See you in Ulm in April.
Yes.
In the next Coiltech exhibition. Thank you again.
Thank you.
And we have concluded the technical webinar. I thank again all the speakers and the attendees. And I'd like to announce the next interesting webinar entitled Battery and Electric Vehicle Charging, scheduled on February 2 of the next year. If you like to present a contribution, you find in the chat the email to submit your proposal. Thank you again. I leave the floor to Dr. Kuster for the conclusion of this event. Please, Sebastian.
Thank you, Marco. First of all, for your competent chairing of the session and for the announcement of our next webinar, which will be then almost 3/4 of the way between Ulm, Pordenone and Ulm. And we think that it's a very good teaser occasion for the community to prepare for Ulm. Of course, I want to thank for today, first of all the audience that you joined us for your questions. I'm very delighted that there are more questions asked than there was time to answer now. So great that we have the chat function so that you can discuss it with the presenters. So thank you, Dragana, Popovic, Andrea, Credo, and Fredric, Wigh, for your interesting presentations, and congratulations to this resonance. I would follow up on what Marco just said and suggest that besides putting the webinar on your agendas, save the dates for Ulm, 6 and 7 April in 2022. Then we are co-organizing the WMM conference, which together with WINA, that will be held from the 13th to the 15th of June in Milan. well, with a very nice and interesting program in the evenings. There will be more information published soon. And then, of course, on the 28th and 29th of September in Pordenone at Coiltech. From now on, the director switches the chat function online so that you can get in touch with each other and discuss the questions. This option will remain open until more or less 2 p.m. and after that you can use the chat the Electric Motors Talks session. Now, oh, my wife's calling. See? Pronto? Ah, it's okay. Yeah, okay. I finish. Yeah, we have finished the session. Yeah, thank you for telling me that it's enough now. Okay. Yeah, I come to lunch. Okay, see you soon. Just a second. Okay. My wife told me that I should finish now. That I've talked enough. So I will follow this advice and wish you a very good time and see you in 2022. Bye.